I worked for a company called Compass, or Massachusetts Computer Associates, for something like 11 years in the 80s when all of the supercomputers were big in a previous life. And did compiler work there for the connection machine and MassPar, numerics, Alliant, some government contracts and the like. And there I learned what a mess the world was. I then went back to school to try and straighten the world out. I ended up at Digital Equipment's company's Cambridge Research Lab in Massachusetts. That got bought out by Compaq and then HP, and then HP dropped that lab, and now I'm at Intel with some of the others in that lab. So that's my history. And I guess, in fact, every step along the way had some impact on what's happening here, what I'll talk about today. I just realized that these slides have the names of Mario Delman and Frank Schlimbach, who are my colleagues in Germany, who were here visiting and sharing this talk with me and doing some training elsewhere earlier in the week. But I have a slide in the end with the full group, so it's not just the three of us working on this project. And the topic today is boxes and circles and triangles, and if you know what they are, then you can leave now. But no, there's a little more to it. This is a very high-level language, so I'm going to start out with the charts and graphs because I'm not going to say a lot about the numbers, but I just want to dismiss the notion, dispel the notion that because it's a high-level language, it's going to be inefficient. That's just not true. And these are, this is some work done by an intern who was with me. She is an applications, in the applications field, and she's at Georgia Tech with Rich Vudak. So she did some cholesky experiments. These are the matrix sizes here, and these are the performance numbers, so higher is better. This is the serial performance. These three are Silk, OpenMP, and ScalarPack down here. And up here, CnC is this one, the red one here. And that's up there with multi-threaded MKL and Plasma. Plasma is being done at Oak Ridge. You probably know about Plasma. Shotgun Dara, right? So she won the Best Paper Award at the recent IDP this year for this work. So cholesky is a piece of the eigensolver, so it's used, I think, 3 different times within the eigensolver. So the eigensolver is quite a bit bigger. And here's the baseline. Here's multi-threaded MKL, and here is concurrent collections. So it performs well. I should say I'm hoping this is interactive. It's a small group, and I'll take questions anytime. Just shout out. Okay, good.
You're only doing on one 2-socket 4-core processor, or is this
for these experiments? For these experiments, that's what we did. You know, we certainly plan to work on bigger things, maybe with your help.
The MKL's on version 11 now. Do you know if there's a significant difference in MKL 11 and 10?
No, I don't. I do know that we're in discussions with the MKL group, and there's some possibility that they will use this approach in some of their library routines. So they've expressed an interest. Anything else before I move on to say what the model is? Okay. So from my compiler experience, I have a kind of a different take on what the problem is, what it is we're trying to address. And it's quite different from the usual, the other models out there in a couple of different ways. But let me introduce it first, and then we can talk about what the differences are. So this is my perspective on the problem. So most serial languages are over-constrained. They're explicitly serial languages. So if you have two computations, A and B, and there's no required ordering, in a serial language you need to put A and B in some order. And that's unnecessary, and then the compiler has to try to figure out that they don't need to be in that order. And sometimes that's easy, and let me tell you, sometimes it's not. They also are talking about location, so particular location in an array, for example. So they may have multiple definitions of an array location instead of having talking at a higher level of just values. And so if you have a definition and a use and then another definition and a use, you may be able to, the compiler may be able to figure out that you can invert them this way, but the possibility of doing them this way might or might not be valid. And so that's an over-constraint. And the programmer probably knew what the answer was, but the language they have to write in doesn't allow them to tell us. The other issue is that as you're going through the program with your control flow, you get to some point in the control, you're about to execute the next block. There's a question of if you're going to execute the code and when you're going to execute it. And in that world, the answers to both of those questions are bound together. So the answer is yes, you are going to execute it because you got right there in the control flow. And the answer to when is now. So just as you produce data, some point in the program, you consume it some later time, not necessarily immediately. We'd like to produce the decision that something will happen, and then later on have that thing happen, and sort of break apart those two questions. So most parallel languages then are embedded within these serial languages. So they inherit all the problems of the serial languages. And then in addition, they are also over-constrained in a couple of ways. One is that they're too specific with respect to the type of parallelism. Maybe data parallelism is what they do, or fork join parallelism is what they do. And they might be specific with respect to the type of target. Maybe it's designed for distributed memory or only shared memory or something like that. And yet, with all of these constraints, they still don't provide enough for the tuning expert to really have control over what's going on. So, so that's the goal. So the solution is to raise the level of the programming model just a bit. In fact, it's too low. The level is too low because it's explicitly serial or explicitly parallel. And we'd like to raise it to stating only the semantic constraints and nothing more. And that's what we're going to do. So I've told you, but I'll tell you a little more about what the big idea is. But then we'll go through some simple examples at the language level, and then we'll talk a little bit about the execution. So the idea is you don't specify what operations happen in parallel. This is difficult. Might not be difficult for you, but for a lot of people it's difficult. And it also depends on the target, and that is true for you. I take it you're quite aware of that problem. And in addition, instead of doing that, instead of specifying what operations run in parallel, we'd like to specify just the semantic ordering constraints and nothing else. So these constraints are easier. You have to know them in order to write a correct serial program. And in addition, they apply to the application only. They don't have anything to do with the hardware. So they're simply semantic constraints. So the semantic constraints, well, that's what I said. It's the meaning of the program. They require some computation. The program itself requires some computations to occur before other ones. Not the program, actually, the application, has some inherent ordering. So what are the two sources of these constraints? Well, there's the producer-consumer relationship. So if you have a producer producing some data and a consumer consuming it, then that producer has to execute before the consumer. That's pretty straightforward. And there's a controller-controllee relationship. If one computation determines whether another computation is going to execute, then the controller has to execute before the controllee. That's it, basically. So what this leads to is quite a more significant separation of concerns than we have in today's languages. It's not a total separation, and there is some communication still required between the domain expert and the tuning expert, but there is a lot more separation than you might have thought or than existed in the previous world. So the domain expert doesn't have to know a lot about parallelism. They have to know about their application, and they don't have to know anything other than what they already need to know to write the serial version, but they do have to write it a little differently. So what they do is write a specification, a concurrent collection specification, and the goal is that that specification is the mapping of the abstract problem down to these constraints. Then as a separate activity, there is what we call the tuning expert, takes that specification and maps it to the target architecture. These are two separate pieces. So the tuning expert doesn't need to know a lot about the domain. And the work of the tuning expert is dealing with the architecture, the actual parallelism, locality, overhead, load balancing, distribution across the processors, scheduling within a processor, all that stuff that we know and love.
So the tuning expert is, in your view, a person or is a one-time system?
Great question. I didn't plant that question, but it's a great question. The tuning expert may be the same person at a different time. So even in that world, they can think for one time only about the domain and then switch hats and think only about the tuning. It might be another person down the hall or in some other country or whatever, who actually knows a lot more about tuning and less about the domain. It might be a serious compiler that does a lot of analysis and figures out exactly what to do, or it might be a dynamic runtime. But all of that we'll call the tuning expert, because what it's doing is it doesn't know anything about in all of those cases, it knows nothing about the domain or very little. Or doesn't have to think about it much in any case. But their focus is on getting the tuning for that particular architecture. Anything else? Okay. So the domain expert doesn't need to know a lot about parallelism, and the tuning expert does not need to know a lot about the domain. When there is some interaction, it's at the level of this specification here. So you don't have a million lines of code to deal with. You might have 3 pages or a page and a half of the specification to deal with, and you can communicate at that level, and those are the things that you need to know about. So what's the variance in the data size of this particular data structure? How big is it usually, and how often does it stray from that typical, things like that, or how long does this step typically take? But you're talking about the specification, not about the whole code. Okay, so we have some notation. There's a graphical notation which looks kind of like boxes and circles and arrows. So when you go to the board and describe your application to your colleague, you're probably drawing boxes and circles, and you draw arrows between them, and these are the things that you're discussing. So foo is a computation. We call it a step, a computation step. X here in this case is a data item. And the textual notation is designed to correspond to how you draw on the board. And now we have this other thing called control tags, which I'll talk about in a minute, because that's the new thing here. That is a little different. Are there questions here? No. So in this notation, the producer-consumer relationship is written like this. So there's step 1 is producing a particular item that's consumed now by step 2. So we have arrows between them. So this is what you might write on the board talking to your colleague. And the controller-controllee relationship, step one is producing some control information into a tag collection, a collection of control tags. And this producer relationship is similar to this producer relationship, so it's just producing something. This relationship, on the other hand, is different. And the meaning of that I'll tell you in a minute. But basically, this says if there's a tag here with a certain value, then that step, having access to those values, is going to be executed sometime. So that's the control information. And I'll tell you more about that because, as I said, it's new. So the way I'll explain the tag collections is by starting out with a loop here, a loop nest, and the body of the loop. So we have an iteration space here, and this is, you're probably fairly comfortable with this. So there's an iteration space here, and as you're going through this loop, the iteration space is produced one at a time. So it's 111, 112, 113, et cetera. And as you produce each one of these, you then execute the body of the loop immediately. So it's an ordered sequence of these tuples, and you're executing the associated body. And as I said before, the if and the when are tightly bound together. Okay, so if we want this to look, to show what this actually means, then this is the thing being controlled. That's the equivalent of step 2 up here. And this is the set of indices. And step 1 is producing those set of indices, but we're going to save them in this tag collection called T2. Okay? So now it's not a sequence, but it's an unordered set. So what that means is you're going to put tags into this tag collection in some order, each tag at some time. It doesn't mean that you're going to execute the code immediately or even in that order. The order is then constrained also by data dependencies, but it's not in the order that necessarily that you put the tags into the collection. So these things, I, J, and K, are the tag components. So T2 is a tag with 3 components, a value for I, a value for J, and a value for K. And when step 2 executes, it has access to those values in the same way that this loop body over here had access to the I, J, and K values. Okay? So, the one other thing is we're not talking now just about integers. These things can be, graph nodes or tree nodes or sets of elements or anything that has an equality operation in your domain. They're supposed to be meaningful in your domain. We know nothing about the types. We don't pretend that we're going to have any access to the types, but you do need to provide us an equality operation. Okay, so this is just to point out that there might well be loops, and here's a data dependence that also further constrains the ordering. But in this case, it might fully constrain the ordering. But so the fact that a tag is put into this tag space just says that this will execute sometime. It says nothing about the ordering, and the data dependencies further constrain the ordering. So. Well, it constrains the ordering in that you're probably not going to execute this step until that gets, the tag gets put there, although we can also deal with speculation, although we don't have it implemented yet. So the grain of the step is under your control. So it might be the case that the 2 inner loops are within a step. They're not outside the step. So the step 2 then will take more time. It's a bigger computation. And the tag components, in this case, will only be K. So there'll be fewer instances of tags, but they'll represent a bigger piece of work. And that's all up to you. So that's another place where the the target creeps in a little bit. You can use the same language, and a grain size decision, first of all, can be parameterized, and secondly, it varies much more slowly than the type of parallelism, or whether you've got shared or distributed memory, or that's we'd like to get rid of that issue, but it is still there. The other thing to say about that is we're working on a hierarchical variant, which would have some impact on this. And I did have a student who did a thesis on dynamically adjusting the grain. So we're on the case, but we're not there yet. Whoops. Okay. Oh, I'm going backwards. Okay. So some simple examples now. So I'll start with cholesky. So cholesky, you're probably familiar with, it's an array computation. There's a serial cholesky. Here's another case. You have to tile. We're preparing for parallelism. So if there's a parallel algorithm that's a tiled algorithm, you still have to tile in order to get some value out of that. There are people doing research on how to automatically tile, and we're some of the people doing some of that research. But in the current system, you have to tile it. But you don't have to. You still don't have to think about what goes before what. So you have the serial cholesky over here. Each of the tiles in the same column do a try-solve computation, and then each in the lower triangular part over here do an update based on the same row, I guess. And then, I shouldn't say and then, but in addition, you do another serial cholesky, and you continue on like that. So to understand how to put together a concurrent collections program, I have kind of a recipe that you follow. So we'll walk through the recipe. So what are the high-level operations? When you go to the whiteboard and describe to your colleague, what are they? One is cholesky, one is try-solve, and one is update. The next question is, what are the chunks of data? Well, in this case, it's only this array over here. The next question is, what are the producer-consumer relations among these computations and the data? And here, all three computations are updating the values and getting old values out. And the last question is, what are the inputs and the outputs? Well, the inputs and the outputs we represent as these arrows here, and the idea is that those are in fact, producer-consumer relationships, that the environment is producing values to be used by the program, and the environment is consuming values to be used by the program. Yeah.
So at this point, do you need to know the tiling of the data, or is that?
Well, the tiling is parameterized, likely, but you do need to tile it. You're kind of getting ready for parallelism. It's making the thing parallel ready. Not all algorithms are tiled, but if you want to use a tiling approach, and this is one of them, then you'd have to tile it. So automatically tiling it is something people are working on now. We don't do it yet. Okay, so you might write that previous thing to your colleague, as they say on the whiteboard, but it's not precise enough to execute yet. So what do we need to do to make it precise enough to execute? We have to ask a few more questions, not many. So one of the questions is, how do we distinguish among the instances, both the instances of the computation and the instances of the data? So the idea here is this is not a streaming style computation where you have, it's not necessarily a streaming style computation where you have a computation somewhere and the data is flowing through it, but we want at least the ability to take each of the instances and place them across the machine and across time. In order to do that, we need to distinguish what these instances are. And so it's a single assignment form where each value is going to have its own identifier, its own tag. Now that doesn't mean it executes that way, but at the level of the description, which we want to be independent of the target, you do write it in this single assignment form. So for example, iter, which is usually not seen in the array dimensions, you're gonna actually put here so you can distinguish between the values in different iterations. Okay. The next question is, what are the distinct control tag collections? So it turns out in this case that each of the 3 computations is controlled by 3 separate control tag collections. That's not necessarily true. You could have a collection that has identified financial options or genes or something like that, and you want to do a couple of different things with each one of those. And we'll see some of those later. But in this case, we have a collection for each. So what steps produce these? In this case, we have the iteration space for cholesky coming from the outside, the iteration space for the trisolve being produced by cholesky, and the iteration space for the update being produced by trisolve. So that's all you have to say, and nowhere in that discussion have we ever said anything like, can you do this trisolve computation for the next iteration at the same time you're still doing updates on the previous iteration? I mean, we never had any of that kind of discussion, and yet if you execute this right now on our multi-core system, that in fact will just happen. So, pardon? Oh, okay. So we're essentially making this ready for parallelism. We are not talking about parallelism per se at all, and we're making it ready for any kind of rescheduling, in fact. So if you're interested in rescheduling for power or rescheduling for locality on a uniprocessor for the memory hierarchy, we're talking about rescheduling, and this language would be totally appropriate for that. Parallelism is the hot topic of the day, so that's the focus of the talk here. So without talking about parallelism, we get deterministic results and in a race-free way. Okay. So I think I have 2 more examples. This one is very quick because I'm not going to show you any details. This is the whiteboard level, basically, with some identifiers about how you distinguish these. This is a cell tracking algorithm where these are biological cells, and they're watching them grow and die and divide and move around. And so they're tracking them under various different conditions and trying to see what conditions they do what. They had a serial algorithm that was published, and in the process of talking to them about this, we found a couple of errors in their serial algorithm, which is nice. So it's not even clear where the parallelism is here, but there was. So the first question after what was the whiteboard drawing essentially is, what is the control space here? Well, K is the number of the frame coming into this analysis. So there's a video frame number, which is K. And of these 6 computations, K controls 4 of them. The other 2, which are the correction filter and the predication filter, actually are done once per frame per what they think might be a cell on this frame. So there are many more instances of those. And the computation that produces this tag collection that controls this is in fact this arbitrator initial function. So it produces this collection which then controls this. Okay, whoops. Then there's another collection down here which has a similar function, but the values are slightly different. So this is a new and improved set of cells that it's finding on the from this computation. It's reassessing what it thinks cells actually are. And so then you're doing another computation down here. So that's that one. Any questions there? No. And this, I think, is the last one I'll show you. This is a face detector. So the idea here is that there are frames. These might be either still frames or video frames. But they're looking for a face. And when they take a frame, what they actually do is look in all possible square windows in that frame. So if you can think of starting from any pixel, and imagining that that pixel is the upper left corner of a window, what are all the square frames square windows that you could make out of it? So there are a lot of them. But I'm just showing a couple here. So this is the one window. This is 4 overlapping windows, and this is 9 non-overlapping windows. But so they can be whatever. And the idea behind this is to minimize the computation because it's very intensive by having a cascade of classifiers. These classifiers are generated by machine learning, so I don't actually know what they do, but there can be hundreds of them. You could think of them as the first one checks to see if there are any eyes. If there are no eyes, then it can just be dismissed as a non-face right off the bat. So, and then it eliminates any further work. And the idea of the machine learning is to quickly eliminate those things that can be quickly eliminated. So up to the whiteboard drawing, we just have this image, and we have all this set of classifiers here. And the consumer relationships, there's no producing here at this level. And then we go to the next phase, and all the work here is done in the tags. So this initial tag set is all the windows of all the frames, and they might be coming in continuously, the frames. Classifier, for any window in any frame that classifier 1 checks, it may or may not put out its own tag. So if it gets in frame 7, window 38, then it may or may not put out 7,38, but it won't put out anything else. So what that means is that these are a sequence of subsets of each other. And so there's less and less work to be done on each of these. So what's the parallelism in here? The potential parallelism, you could do a bunch of classifier 1s. There'll be plenty of parallel work to do when you do that because all the windows are. You can do all the classifier 2s. There may be a lot of work to do there, but when you get down to classifier 100, there may be pretty much nothing left. And it's hard to tell if you should be doing that in parallel. Or you could have a stream of these going down, so you have a pipeline of them. Or you could look at how many there are in each of the tag spaces, how many are left to do, and decide which is the appropriate bucket to pick up of which classifier you should execute. So there are plenty of different ways to parallelize this. You could separate the tags and do the frames in parallel and the windows serially, a zillion different ways. And which way you choose depends, as you know, on the architecture, but the semantics is all that's written here. So this gives you the constraints on the problem. So basically there are these...
Did you say in the beginning that the actual order or the dependencies are should not necessarily set in the beginning? In this particular case?
Oh, they're dependent on the data. These are dependent on the data. So in this case, it's not statically known. We can't do a...
But I mean that T1 comes before T2.
Oh, T1 comes before 2 for the same window on the same frame. But you can do T1, you can do T1 after T2 if you're doing a different window or a different frame.
Okay, but the programmer chooses the order T1, T2, T3.
The domain programmer just writes the constraints like this.
But like checking for existence of eyes before you check existence
So,
of mouth.
So the programmer writes, you know, the programmer, well, in this case, it's the machine learning tool, I think, that writes, you know, each of these classifiers. And they have to then make it, I'll show you how they do that. They make it look, they make it works to input this image and output maybe this tag, depending on what happens. So there's a little modification to the code to make it work in this environment. But then the domain programmer specifies just these constraints and gives it off to the tuning expert for this machine to decide how to execute it on the machine. And again, the tuning expert could be a person or a static analyzer or whatever. Is that the question? Yeah. Okay. So we have these three objects. There are steps and items and tags. The steps themselves have tags. They are tagged. They perform put and get operations. We assume that they are functional in that they have no side effects that are visible outside. Right now, this is a verbal contract, and we're hoping to get more checking in there. But at this point, it's just, this is how you should write the code. It's that they're functional, that the steps are functional, and that the data is single assignment that gives us this determinism. So the items are the means of communication between the producer and consumer relationships. So they have to be in this dynamic single assignment form, and the items are also tagged. And the tags are the means of communication that represents the control dependence. And that creates our ability to distinguish the if from the when something's going to execute. I guess that's it there. So there are three types of objects, and there are three types of relations. There's the producer relation, the consumer relation, the prescription relation. Prescription is our term for control. And in the cell tracking, for instance, there was a control collection that represented the different frames that were coming in, and it controlled more than one computation. I think it controlled 4 computations, right? So that's possible there. For the consumer relationship, it's possible for a step to consume from more than one item collection. So a step can do a get on X's and another get on Y's. And even within a collection, a step can do a get on a number of different elements. So you can do a nearest neighbor computation. You can get north, south, east, and west. You do like that, whatever function you want to write here. Okay, and similar is true for the producer relationships. They can produce into more than one collection and put more than one item in a collection. So between any two steps, there are only 8 different things that can happen. So 4 of them are here. It's possible that there's a data dependence or a control dependence. Whoops. So in this case, there's both a data dependence and a control dependence. In this case, there's neither. Here, there's just a control dependence. And here, there's just a data dependence. Okay. Now, this was when we have 2 distinct step collections, and we're talking about instances between them. But the other possibility is that these 2 instances are, in fact, in the same step collection. And we get the same 4 possibilities. They can have both. They can have neither. So since this is from one instance to another, you don't see any cycles here. They can have just a control dependence or just a data dependence. And I'm not sure, we should be over at 2, over at 3. Oh, we have plan.
I will have to step by out.
Oh, okay. Oh, okay.
That's why I've been looking. Otherwise, there will be people looking for me.
Okay. I'm trying to think if there's. There are a few slides at the end that I will, am I going to see you later? I can just show you.
That's the problem we have to prepare for the video.
Ah,
So I
okay.
have to
Then
go
what I'm
to-
going to do, I think, is to,
Come to the end and jump back.
should I do that? That will screw up this video.
Does that make sense for everybody, or?
Well, why don't I go through it? I mean, I think it'll make more sense if I go through it.
This
Yeah.
stage is seeing the relationships here and the dependencies. Supposing I just create a big thread pool and I assign lots and lots of job, effectively, batches, and
Right.
threads take those jobs, and the dependencies are encoded in the description of the thread and the description of the job, because I know that I can't operate on this until that's done, and the threads know that, and they're kind of independent. Is the advantage of your, because it seems to me that would effectively do exactly the same thing. The advantage of this is that it's somehow specified in the, I mean, would this produce a different result than, say, a traditional thread pool with work stealing kind of approach?
Okay.
Or is it just that it's explicitly defined in the language, if you follow me?
You're defining it explicitly. So one thing that we can do here, we can do a lot of different things here. This just defines the constraints. So in the back end, we could have a runtime system which does kind of what you're talking about. We could have a runtime system that maps everything statically, distribution and scheduling, and does all of that statically if the computation is amenable to that. We could have something that works in a shared memory system, in a distributed memory system. All we're specifying here is the constraints. What you're specifying there is maybe one of the possible runtime systems that we could have. And because it's at a lower level than this, the user...
set of all the possible ways of handling that.
I think so. So maybe, I believe that's the case. If not, let's talk after. So I think, and the user doesn't think about threads here. We have no, we haven't said anything about threads. We haven't said anything about where.
When you create a thread and you add it to the thread pool, you inherently know the conditions for that thread to run must have completed, because that's the result of the previous thread that's just finished doing something. And then you say, okay, now I've finished this job, but I can now give that job into the thread pool for completion whenever it wants.
So
But you don't put it into the thread pool until the conditions for it to run have been met, and that naturally is like a tree which flows out, which objects get created as and when they can be created, and they get executed whenever there's something available to do it.
So our current runtime system works very much like that. It sits on top of TBB, but it's much easier to write than, for the domain expert, it's a lot easier to say. They don't have to talk about threads at all. They don't have to worry about changes in their environment.
So one question that I would like to see answered before I leave, or
Okay.
the next 10 minutes, is now, what does this look like to the programmer?
Okay, good.
Cool. I know probably that it sounds forward or
That's okay.
or,
I can do that.
and I mean to the domain.
Yeah.
So,
Uh,
or is this embedded in some host language?
Well, the thing,
So,
so it's, we have a bunch of different implementations. The one that's on the website is in C++. We work closely with Rice, with Vivek Sarkar, and he has a different implementation. His focus is in Java. That runtime is in Java. We have two preliminary implementations that I'm not sure exactly how real they are. One of them is by a colleague of mine that's in Haskell, and one of them is by someone at Rice again, and it's in .NET. And so in theory, from the CnC perspective, it could be anything. And I know Fortran is a big issue here, a big language. And we've been talking about a Fortran implementation with our Nashua team who does the Fortran compiler.
So they look different if you do report working for
The step
so they are
code-
part of,
the
so
code
it's an
inside
addition
this-
to the syntax, to the language, host language, or is
So
it
there's
part
an,
of-
the language you write the step in is any of these languages, and then there would be an API call to a put or a get, and some structure that says this is a step around the outside. But I'll show you in a second. If we take a look at this little piece of the subgraph for the cholesky thing, the producer-consumer relationship here is represented here by an arrow. So since this is square brackets that has an arrow into these parens, this is a consumer relationship. So try-solve is consuming the array. In this one, try-solve is producing the array. Here we have a comma, which means that this try-solve is consuming both of these instances, for example. So the control relationship, which, whoops.
So you're extending the syntax of one of the host languages?
No, this is just a language in and of itself. It's a tiny language. So whether you...
Well, when I introduce this into a program...
I'll show you how it goes. This is just this dotted line here. So this represents the control relationship. And then in addition, we have some declarations which are types. So here the array subscripts are integers, and this is the type of the contents of the item. So this is a language in itself, and what we do is take this and translate it for you into something that looks like a step. So we know from the relationships here that this try-solve step is going to do a get on the array. And what it's going to produce, we don't know what you're going to store it into, but we know the type of the thing you're going to store it into. So we give you a hint here that that's code you need to put in, and we generate this, without just standard stuff. And we also know that you're going to do a put of the array. We don't know the tag yet, but we know you're going to do the put, and we don't know the name of the local variable here that's going to have those values. So we can tell you that this is the form of your step, and then all your implementation logic goes in your language, which would be, in this it's going to be C++. But if for the Java thing, this generates Java.
As a programmer, I write what was on the previous slide, and then the system generates a skeleton.
Right.
Okay. Into which the
and then
programmer then puts in C or so.
Now it's a little like so then there's a class library that implements CnC, and you can write directly in that class library. So that's why when you said, is this a language, I said, it's kind of a model to me. So you can get into it by writing directly in the class language, which you might want to only do after you've done this a few times. You can write in the specification language, which gives you some nice documentation, and as the project proceeds, we'll have more and more static analysis and checking and error, locating stuff like that. Or we also have started, an intern with us has started a GUI that looks like boxes and circles, and so you can drop and drag and create it that way. But the model is still the model.
So you have a way, I think I kind of get the picture, but the question is now, where do I as a programmer enter with debugging?
Okay.
Can I debug at the level of your meta language or whatever you call?
Wonderful question. Right now, what I would like to do is have a debugger which is exactly at the level. So you say step through the program, and what that does is execute a step, a CnC step. And you might provide whatever you want for visualizing a data item, whatever that would mean. And you could set breakpoints at puts and gets, and it's sort of understand this higher level. We don't have that yet. What we do have is some tracing facilities, and you can always use your standard debugger. The same story is true with performance. Intel has a lot of performance tools. You can use all of those performance tools on this, but I'd like to have a performance tool that knows about CnC and is at this higher level and says, you know, this producer-consumer relationship is the one that has all the communication associated with it. So I definitely like to do that. And the rest of the team is anxious to do that as well. So let me see.
But then you generate this code, and the user, the domain expert, is going to write in some
Yeah,
code.
right,
And then you end up with the C++ code in this particular case.
right.
That you put through a compiler.
That's this thing. So this green is the user code. You put in the textual graph, if that's how you're getting into the model. And you also put in, you know, after the textual graph creates some hints file, or maybe directly, you put in the code for your steps. This does a translation which produces not only the step framework, the skeleton, but it also produces some header information. That gets compiled, I have to say, by any C compiler. And we also link that with the existing CnC library. Okay, and that comes out. I hope I answered all your questions.
A final question, and then you have more time.
Okay.
Okay, is this going to work on Intel platforms or within the Intel, or you're planning to make it like, could I use it together with GCC, G++, and you know,
Yes.
whatever Linux
Yeah.
system that is?
So we have a Linux and a Windows version of the runtime, and this is any compiler. So that will work fine. We don't have a Fortran version.
Yeah, okay.
Yeah.
Well, that's a detail then. Later.
Somebody
Yeah.
has to worry about this.
Yeah, yeah.
So I think, but I think given that we had,
Yeah.
yeah. Okay, so I was at the 8 different relationships here. And I'm going to show you examples just from 2 of them. So this one is the relationship where there's 2 different steps and there's a controller-controllee relation between them. So what might that be? It might correspond to what you think of as an if statement. So S1 of J is producing, maybe or maybe not producing T2 of J. So it will have access to this, if it executes, it will have access to exactly the same control information. It might be that this S1 is occurring within the context of an outer loop, and for an instance of that outer loop, it's producing an inner loop. So if you have a K loop and you want to put a J loop inside, then for each value of K, you're going to produce a bunch of values of J. So, oops, I use J and I here, but I think you can translate, right? Another option is that you have some tag controlling the step, and you're inputting data, and from that data you're producing some entirely different tag that's probably data dependent. So, so this one thing just says S1 controls S2, but it doesn't say exactly how. But when you write it in this form with the tag components and the tag functions, which tell you how to transform the tags, then you get some more concrete information about what's going on. So here's one more, which is interesting. This is the second one, and I won't talk about any more of them. So this is, the 2 instances are from the same step collection, and there's both a control and a data relationship between them. So suppose this is a while loop, and here's some code from a while loop. So you have the body of the loop, you have some data, and you have the control. And the input to the while loop is the initial value, and I think this is written in white up there, so you can't read it, I'm sorry. In addition to producing some more data, it's also producing some control. So If the if test passes in the while loop, it's probably put out some data and it's going to put out a tag that says do the next instance. Okay? And you're probably going to put out the output items, or at least the final one, and you may also want the tags for some reason. Okay, so that's a while loop. But this same story goes with a divide or divide and conquer. Yeah?
So does your language have a feature to detect endless loops?
No, you can write an endless program, and in fact, you can write a program that has finite input, and you can write an endless, or even no input, and has an infinite loop in it, and that might not be an erroneous program. That might be exactly what you want to compute all the primes. You know, you don't need any input to that, and you just go through forever, right? Or you might have a program like something that does video, some kind of video detection, surveillance or something, that just has continuous input, and that's the intent of the program. So for finite, we do have at least one continuous program. There are some issues, including how you know something is dead, which are not well addressed in the continuous program, and you can't go on forever. You know, unless you reclaim. So there are some interesting issues there. So we would need what I call a different variant of the language in order to support that. But there's, that's the other reason that I don't call it a language, because we have a bunch of different variants in mind. One, for instance, that does continuous application. One that, so that's a little broader than the language I presented. A little more constrained is one that only deals with totally analyzable relationships. So if the functions that relate the producer and consumer to the step then are totally analyzable, then we might want to have a variant that only allows that. And there are other variants as well that we might have. We have a customer, a potential customer, who's interested in real-time scheduler, and so that's fine with us, but we might have to make a variant for them. So it's a model as opposed to a language in that sense as well.
So there was an earlier comment you made about race-free
Yeah,
support.
that wouldn't be true in the soft real-time. Oh, how do you do that? Because
How
the...
did you claim that? How did you prove it to yourself?
we have a proof of it, actually. I don't know if you know Jens Paulsberg. He's a theory type in the programming world, and he has a nice proof that because of the dynamic single assignment, you can never produce, each value is associated with only one, each tag is associated with only one value. Because of the side effect free aspect of the steps, you can't do anything in one schedule that you wouldn't have happened in a different schedule. So, so you'll get exactly the same thing whether you execute on a uniprocessor, on a GPU, or on 1,000 cores, or whatever.
That effectively means that every step executes with a completely localized memory model that is not allowed to.
In theory, that's true. As I said, right now we don't do any checking to make sure that that's true. So it's a verbal agreement. It's right. It's stated clearly, but it's right now we don't do any checking.
Provided the programmer behaves himself.
Yeah, right. If you're a good boy, we'll take care of you. But what that means is there's a programming bug if there's a race. Well, it always means that, but it's a local bug within a single step that is causing the problem. It's not an interaction between two of them.
Do you add any kind of, I'm still thinking of kind of thread pools, prioritization, so that these things can happen in any order, but if you did this one first, it would be kind of useful.
Well, that's entirely, that is the role of the tuning expert. That's the tuning expert. And whether it's a scheduler or a person or whatever, that's their role, to map dealing with priorities. We have a priority-based scheduler, except that we...
But hold on, there's never been any mention of any kind of prioritization in any of the syntax that you've shown us. So
Right,
is that
this is-
specified as an
That's why that's why this is a different slice across the problem. So we have a single language that allows you to describe your domain. And then, although we might have we're working on a language which would apply for scheduling across domains, but on any particular hardware, you may well want some very special purpose kind of scheduling, like these people who want a real-time scheduler, and that's perfectly fine. All we're talking about at the domain level is the constraints. So we haven't said anything about scheduling yet.
But in your compiler, you do have a schedule built in, so
We have 5 of them.
so you can choose between them.
And that's, well, we have 5 of them and we can choose between them. I would like to make that option freely available to you. Right now, it's not. But one of them is a priority-based scheduler, which we're happy to feed through your priorities, but TBB isn't happy to do anything with them right now. So that doesn't work too well yet, but it might. Anything more? Should I go through the divide and conquer? Okay, so remember the while loop. So here's a divide and conquer application, and again, this here looks very much like it did before. So we have the code in the middle, there's some tag collection that defines it, and an item that's consumed. The root tag and the root item are probably coming in from the environment or from somewhere else in the code. And then when the divide happens, instead of, as with the while, instead of putting out one item in one tag, it's probably putting out 2 or 3, so it's putting out its children. So it might be right child, left child for the tag, and for right child, left child for the item as well. But this, and then you probably want to output the leaves. And this looks a lot like, if you squint and you don't look at the tag functions, then it looks identical. So, and in fact, if you look at a conquer part, it again looks identical at this level, but the conquer step is now, in fact, going to be taking in 2 children and putting out 1. So it's a little different in that sense. And you probably want to connect these 2 up. So you want the leaves of the tree going over here, and the leaf tags going over there as well. Okay, so divide, conquer, and while all look identical. Okay, so this is the part I just went over before, so can I skip over that? Okay. So we have a runtime library in Windows and Linux. We have this translator that creates the hints file for you. We have a Visual Studio integration. We have some documentation. There's some samples on the web that you can look at. This is the build structure that I defined before. This is sort of doesn't need to be said, but we do sit on top of the thread building blocks in this current implementation. So these are all the ways that I don't think of it as a language, as a model. So it's the textual representation. You can write directly in the class library, and you can write in the in this graphical interface. And also we have this idea of a number of different variants. And in fact, some of the implementations that we've had, starting back when this started at HP, have had quite different trade-offs between efficiency, ease of use, generality, and the kind of guarantees that we can make, and probably a few other things. So making different set of trade-offs would probably be a different language, but the same model. So these are the 3 variants that I talked about before. So this is how you think about the execution of your program. The program is declared in this declarative way, and so you need a way of thinking about what's actually going on. And the way I think about it is that as you execute the program, the state of a given instance, an instance of a step, an instance of an item, or an instance of a tag, goes through some different stages in its lifetime. So they start out with having no attributes. They don't start out, I guess. And when they acquire an attribute, you might think of them coming into existence at that point. So an item instance may become available at some time. If a step produces an item, then that item is available. If a step produces a tag, then that tag is available. So these dots just represent an attribute that the instance acquires. Steps are a little more complicated. So this is the same step. As it goes through its lifetime, it may acquire distinct attributes. So it can be prescribed. That is, its control can be available. It might have its inputs available, and those can happen in either order. There's no particular order it has to happen in. But when both of them are true, then we call the step enabled. Enabled just means it's ready to run. It's supposed to run, and all its inputs are there. So it's ready to run at that time, and at some later time, it will be executed. So once it's executed, as I said, an instance comes into existence when it has any attribute. You can think of it that way. And when a step is executed, then we don't have to think about it anymore. So this stage between having some attribute but before it's executed is what we call the execution frontier. It's the stuff that we have to worry about now. And step instances go in and out of the execution frontier, but also item instances go in and out of the execution frontier. So an item can become dead, and a tag instance can become dead as well. So that's sort of the conceptual model. I don't know if you want to go through this. There are three sort of historical models that we sort of have been influenced by. So streaming, data flow, and tuple spaces. And I can go through their properties, or we can skip past this if you like. Interest?
What is the last one you mentioned?
Data flow, streaming, and tuple spaces, like Linda. Shall we talk about this a little?
Well, just a question. Have you been influenced by Arvid's work at MIT with parallel Haskell and implicit parallel programming paradigms?
Well, it is influenced by data flow style, yeah. So if you think about the execution model, it's very data flow style-ish. So there's no extra serialization. You only need to execute when the data is ready and the steps are functional. But we've elevated control to first class. So these tag concepts are first class, and you can compute and manipulate them. Yeah? Do you have a question? No? Okay. So the semantics are data flow, and I describe how I think about the program executing. It's a data flow style of thought. On the other hand, we can have any style of execution. So I don't know if I have this slide here, but you can have a data flow style execution, which is kind of like the one we have now, but you can also statically determine everything, which is one we had at HP, and you can do something in the middle. We had one where the address space was determined by the tuning expert, but the tuning expert who was a person, but the tuning expert who was the runtime system determined within each address space what a data flow style computation would be of the program. So it was kind of a combination of both. So although it's data flow at one level, it's not really at another. Okay. So Here are a bunch of, just to drive home the fact that this back end could be a lot of different things. To define a back end, you might want to define 3 different things: how the grain size is determined, how the distribution across the processors is determined, and how the scheduling within the processor is determined. So at HP, this stuff was called T-streams, for tagged streams. So they had distributed memory systems that they were focusing on. And so the distribution in those was static, was provided by the tuning expert, the person. And we had 2 different scheduling approaches. One was kind of a data flow like within, as I said, and the other one was entirely static. So there was almost 0 overhead in the runtime system. This was only for analyzable programs. At Intel, we have a variant that looks like this. The Rice one looks similar. And we're trying to, as I mentioned, allow you to plug in your own scheduler, but it's not as easy as it would look given the current implementation. At Georgia Tech, I had a PhD student who was working on dynamically adjusting the grain. So we had a totally dynamic system that he built at Georgia Tech, and it was presented at LCPC. So the back end, there's a wide variety of ways that you could do the back end here. And that's all under the purview of the tuning.
So all these would be like CnC implementations in different runtime systems, but the description of the model is exactly the same as
Yeah.
And they all go on C++?
Let's see, the HP one was C++. The Rice one is Java. I think this was C++ also.
But also, if you write on this API directly, like you said you could, then you are totally independent from the language. You just
Well, the API is C++ based. It's, sort of method based. But so we could. So you're thinking of Fortran? Is that what you're thinking?
No, I think just trying to understand the way you express in this model.
Yeah. So in another language, we would have probably an API that has similar functionality, but is written with different dots and parens, and it plays well with a variety of tuning experts. I've already said this a few times. It could be the domain expert only later. It could be a different person with different expertise. It could be a static analysis or a dynamic runtime. We're only talking here about constraints. That's all you write in the language are the semantic constraints. So this maximizes the flexibility for the tuning expert. We don't have any unnecessary constraints here, and we're not only writing those constraints that are relevant for a particular hardware. We're just writing the semantic constraints. So the possible goals include maximizing parallelism, minimizing the latency, maximizing the utilization, predictability, memory footprint, power consumption, anything that requires reordering, and any optimization you want to do on one system that would differ on another system. It might be a good idea to represent the application in this way. The possible styles of parallelism might be loop or data parallelism on the one hand, task parallelism, pipeline parallelism, fork join parallelism, whatever. We have no particular bias in any way, one or the other. All of these are totally appropriate. So I already said you might use it for power or for locality on a uniprocessor even. That would make sense. So it plays well with a lot of different serial languages. We can add Fortran to the ... It would play well with that. I don't know. I don't think it would take a lot, but it plays nicely with a lot of target architectures. So we at Intel have had a shared memory system. The current new release has a distributed memory system on it, homogeneous or heterogeneous, flat or hierarchical. We don't yet have a hierarchical CnC description, and that would work better when we do that. So this is the community I mentioned. The two people that were on the initial slide are certainly on here, but let's see. Jeff Lowney is the head of the group, but it's not that he's a manager. He saw the piece that we brought over from HP, and when TBB was created, he dove in and ripped out the previous scheduler and put TBB in, and then all of a sudden we had a Windows version that we could use. So that was nice. And these other people are also in the same group. This is people from the Intel compiler group. So this is not a product, and there's no guarantee that it will become a product, but it's making its way through that process. And in fact, these people are in the product group, working on putting out the release on the what ifs on the Intel site that I'll tell you about in a minute. And these are the two HP people that I worked with. And these are the people from Rice, from Georgia Tech. This is the intern, and she's working with Rich Vudak. You may have heard of Vivek Sarkar. He does a lot in the high-performance world, right? So he's the one who took this on and is building the Java implementation. And in fact, they have an NSF grant, the National Science Foundation grant, to do some medical imaging work using concurrent collections. And no one at Intel, including me, is even on that grant. So I thought that was nice. Yes, yes, exactly. Yeah, so that's the Java background. He did his own predecessor to X10. I've forgotten the name of it. Do you know?
I forgot.
Oh,
Because X10 is changed now. X10, when he was there, it depends on X10.
Yeah, so this is habanero, and the other one was jalapeno.
Yeah.
Jalapeno, yes, okay. And Nikolai was an intern in our Novosibirsk office, and he's now a full-time employee. He's terrific. And Jens is the theory person that I mentioned who did the proof. Well, I can send it to you, but it's not published. So give me your name afterwards, and I will be happy to do that. And for those of you who like to travel, LCPC, Languages and Compilers for Parallel Computing, is happening at Rice, and we decided to do the second annual CnC workshop there. We had one in Hudson last year, which was the first, and it was quite informal. This is going to be a little more formal, so, but not very formal. It's a workshop co-located with a bigger workshop. So if you happen to be in the area and you want to show up, or if you're sending something to LCPC, drop by, let us know. And so this is where you find the Intel version, and this is where you find the Rice version. On bigger things, maybe with your help.
The MKL is on version 11 now. Do you know if there's a significant difference between MKL 11 and 10?
No, I don't. I do know that we're in discussions with the MKL group, and there's some possibility that they will use this approach in some of their library routines. So they've expressed an interest. Anything else before I move on to say what the model is? Okay. So from my compiler experience, I have a kind of a different take on what the problem is, what it is we're trying to address. And it's quite different from the usual, the other models out there in a couple of different ways. But let me introduce it first, and then we can talk about what the differences are. So this is my perspective on the problem. So most serial languages are over-constrained. They're explicitly serial languages. So if you have two computations, A and B, and there's no required ordering in a serial language, you need to put A and B in some order. And that's unnecessary, and then the compiler has to try to figure out that they don't need to be in that order. And sometimes that's easy, and let me tell you, sometimes it's not. They also are talking about location, so particular location in an array, for example. So they may have multiple definitions of an array location instead of having talking at a higher level of just values. And so if you have a definition and a use and then another definition and a use, you may be able to, the compiler may be able to figure out that you can, invert them this way, but the possibility of doing them this way might or might not be valid. And so that's to stating only the semantic constraints and nothing more. And that's what we're going to do. So I've told you, but I'll tell you a little more about what the big idea is, but then we'll go through some simple examples at the language level, and then we'll talk a little bit about the execution. So the idea is you don't specify what operations happen in parallel. This is difficult. Might not be difficult for you, but for a lot of people it's difficult, and it also depends on the target, and that is true for you. I take it you're quite aware of that problem. In addition, instead of doing that, instead of specifying what operations run in parallel, we'd like to specify just the semantic ordering constraints and nothing else. So these constraints are easier. You have to know them in order to write a correct serial program. And in addition, they apply to the application only. They don't have anything to do with the hardware. So they're simply semantic constraints. So the semantic constraints, well, that's what I said. It's the meaning of the program. They require some computation. The program itself requires some computations to occur before other ones. Not the program, actually, the application, has some inherent ordering. So what are the two sources of these constraints? Well, there's the producer-consumer relationship. So if you have a producer producing some data and a consumer consuming it, then that producer has to execute before the consumer. That's pretty straightforward. And there's a controller-controllee relationship. If one computation determines whether another computation is going to execute, because it's a high-level language, it's going to be inefficient. That's just not true. And these are, this is some work done by an intern who was with me. She is in applications, in the applications field, and she's at Georgia Tech with Rich Vudak. So she did some cholesky experiments. These are the matrix sizes here, and these are the performance numbers, so higher is better. This is the serial performance. These three are Silk, OpenMP, and ScalarPack down here. And up here, CnC is this one, the red one here. And that's up there with multi-threaded MKL and Plasma. Plasma is being done at Oak Ridge. You probably know about Plasma. Shotgun data, right? So she won the Best Paper Award at the recent IDP this year for this work. So cholesky is a piece of the eigensolver, so it's used, I think, 3 different times within the eigensolver, so the eigensolver is quite a bit bigger. And here's the baseline, here's multi-threaded MKL, and here is concurrent collections. So it performs well. I should say, I'm hoping this is interactive. It's a small group, and I'll take questions anytime. Just shout out. Okay, good.
You only do on one two-socket four-core processor, or is this?
For
solid
these
on
experiments. For these experiments, that's what we did. You know, we certainly plan to work on over-constraint, and the programmer probably knew what the answer was, but the language they have to write in doesn't allow them to tell us. The other issue is that as you're going through the program with your control flow, you get to some point in the control, you're about to execute the next block. There's a question of if you're going to execute the code and when you're going to execute it. And in that world, the answers to both of those questions are bound together. So the answer is yes, you are going to execute it because you got right there in the control flow. And the answer to when is now. So just as you produce data, some point in the program, you consume it some later time, not necessarily immediately. We'd like to produce the decision that something will happen, and then later on have that thing happen, and sort of break apart those two questions. So most parallel languages then are embedded within these serial languages. So they inherit all the problems of the serial languages. And then in addition, they are also over-constrained in a couple of ways. One is that they're too specific with respect to the type of parallelism. Maybe data parallelism is what they do, or fork join parallelism is what they do. And they might be specific with respect to the type of target. Maybe it's designed for distributed memory or only shared memory or something like that. And yet, with all of these constraints, they still don't provide enough for the tuning expert to really have control over what's going on. So, so that's the goal. So the solution is to raise the level of the programming model just a bit. In fact, it's too low. The level is too low because it's explicitly serial or explicitly parallel, and we'd like to raise it. Let's see. I worked for a company called Compass, or Massachusetts Computer Associates, for something like 11 years in the 80s when all of the supercomputers were big in a previous life. And did compiler work there for the connection machine and MassPar, numerics, Alliant, some government contracts and the like. And there I learned what a mess the world was. I then went back to school to try and straighten the world out. I ended up at Digital Equipment's company's Cambridge Research Lab in Massachusetts. That got bought out by Compaq and then HP, and then HP dropped that lab, and now I'm at Intel with some of the others in that lab. So that's my history. And I guess, in fact, every step along the way had some impact on what's happening here, what I'll talk about today. I just realized that these slides have the names of Mario Delman and Frank Schlimbach, who are my colleagues in Germany, who were here visiting and sharing this talk with me and doing some training elsewhere earlier in the week. But I have a slide in the end with the full group, so it's not just the three of us working on this project. And the topic today is boxes and circles and triangles, and if you know what they are, then you can leave now. But no, there's a little more to it. This is very high level language, so I'm gonna start out with the charts and graphs because I'm not gonna say a lot about the numbers, but I just want to dismiss the notion, dispel the notion that